Hi there, today we are going to be talking about properties of logs. Okay, I'm going to be doing a few things. I'm going to show you some properties and then I'm going to be going through a couple little examples right here with you. First of all, a little reminder, refresher, you cannot take the log of a negative. Log of a negative number, no way. Can't do that. We also cannot take the log of 0. No way, not possible, can't happen. You can refresh on some of my other videos about logs. Now let's take a look at multiplication property. So let's say we have, I will deal with the exponential properties of exponents. Let's say we had x to the a times x to the b. What we could do here is we could add our exponents because we're multiplying. X to the a plus b. Okay, so I don't know why I put that there. Don't need that. If we have multiplication, it leads us to addition of those exponents. So something very similar if we are dealing with logs. Let's say we had log base x of a plus log base x of b. We could combine these and we would get a single log with the same base, log base x of a times b. So we are starting with multiplication and it leads us to addition of those exponents. One in logs, if you have addition, it will lead us to multiplication. We can do kind of the same thing here with division. Let's say we had x to the a divided by x to the b. Well, division leads us to subtraction, so we would have x to the a minus b. Logs work in the other direction. If you had log base x of a minus log base x of b, well, subtraction should lead us to division moving in this direction. So we could combine them to a single log, log base x of a divided by b. And these make a lot of sense to me because I see this addition sign, and if I think of rotating it 45 degrees, it looks like a multiplication sign in there. Same thing here. This little subtraction sign reminds me of that division bar. So that is a property of logs right there. Let's take a look at some more properties. How about a change of base? Change of base. So if we had log base x of a, we could change this to any base we want. Any base we want. Okay, we could have a log up top and a log downstairs. Like I said, this could be any base you want. 10, 100, 50, you name it. Okay, we can change our base to whatever we would like. Now I look at this log right here and I see the a is in line with the log. The a is actually in a higher position, so I put it in the higher spot up top in the numerator. This x is in a subscript. It is down lower, so that one goes in the lower position. So we could change this to any base we want. We have now successfully changed from base x to any base that you would like to deal with. That is a change of base. How about one that I like to call freedom? Okay. So let's say we have log base x of a raised to the b power. When we have this situation, we have our log there. This b value, it has freedom to move. It has freedom to move down and bounce out in front of the log as a multiplication problem. So it could be rewritten as b, and I'll identify that b there in that circle so you see where it's at. It now comes down out of the exponent position, log base x of a. So that exponent has the freedom to bounce down from that exponent spot to come down out in front. It also has the freedom to move from this position out front when it's multiplication, coming up as the exponent there. Okay, gives it a lot of freedom. Now another one. So let's say we had x sitting right there. We could put an exponent on x. If that exponent were log base x, so the same base of whatever it is that you're taking, those two would essentially cancel out and you would be left simply with a. So our same base right there, if we take our log base of whatever we're dealing with, and if we put that as the exponent on the same base, you are going to end up with whatever it is you're taking the log of. Exponentiation, raising it to the exponent spot. So now I just kind of want to come through and I want to deal with a few different type of log examples and how we're going to be applying these into solving different equations. Alright, so how about we first start off with something like 8 times 4 to the x plus 5 minus 7 equals 9. Okay, so this is just an equation that you want to deal with. We want to isolate our x value. First, I would add 7. 8 times 4 to the x plus 5 equals 16. Divide it all by 8. 4 to the x plus 5 equals 2. Not really the best problem to be dealing with logs with. Here we could be matching our bases, so I apologize for that. But let's say, these were different values here and we couldn't actually match our bases to find the value and we wanted to use logs to solve. Well, one way that we could get this exponent to come down is we would like to give it some freedom. The way that we do that is by taking the log of both sides. Taking the log of both sides is really just writing log in front of it. So now that gives the x plus 5 the freedom to come down out of that exponent position. X plus 5 times log 4 equals log 2. So now I have this multiplication problem. I would undo that by dividing by log 4. X plus 5 equals log 2 divided by log 4. Well, now we could use our change of base properties right here that I talked about previously, and we could change this and rewrite this as a single log. I will also be subtracting 5 at the same time. So x equals, well, I'm looking at this, so I'm going to have a log. Well, the number that is downstairs in the denominator will go in my subscript, so log base 4, the one up top goes up top, so log base 4 of 2 minus 5 would be our solution. We could actually solve this and we could get a value. We could figure out what the exponent on 4 is to give us 2. So we could get an exact numerical value out of this without having any logs in there, but different concept. Well, I'm trying to show you different concepts. So let's see. What else can we do? How about some combining of logs? Log base 2 of x plus log base 2 of 5 equals log base 2 of 15. Alrighty. Well, I'm looking at this left side right here, and I see that we have an addition problem. Addition of the same base, log base 2, so we can combine that to a single log. Log base 2 of 5 times x, addition leads me to multiplication, so I'm multiplying 5 times x, equals log base 2 of 15. Okay, now a lot of people come through and you were just able to drop these same log bases in the same fashion that you would drop the bases if you were dealing with exponents. Same base can be dropped. Really what is happening is we are raising both sides. We are exponentiating. Kind of what we talked about right here. Okay, well, 2 is my base, log base 2 of 5x, well those cancel and you are simply left with 5x equals, well, base 2, my exponent log base 2 of 15, the log base 2 and the base 2 cancel, equals 15. We could divide by 5, x equals 3. Something very, very, very similar to that. How about log base 10 of 6x minus 5 minus log base 10 of 4x minus 1 equals log 7. Alrighty. Coming through on this left side, we are able to combine these two logs, same base, log base 10. Subtraction leads me to combine them in a division. So it would be 6x minus 5 divided by 4x minus 1. Log base 10 of this equals log base 10 of 7. So now, if we would like to get rid of these log base 10s, what we are really doing is exponentiating. So it is 10 with the exponent of log base 10 of 6x minus 5 over 4x minus 1 equals 10 raised to the log base 10 of x. Well, the log base 10 and the base 10 cancel. The log base 10 and the base 10 cancel, leaving you with 6x minus 5 divided by 4x minus 1 equals 7. This is a proportion we can now cross multiply to solve. So I will distribute the 7. 28x minus 7 equals 6x minus 5. Solve that. Subtract 6x. 22x minus 7 equals negative 5. Add 7 to both sides. 22x equals 2. Divide by 22. X equals 2 over 22, reducing to 1 over 11. 1 over 11. All right. Move on down the line. You always want to take these and you want to plug them back in to check your answers to make sure that everything works out appropriately. So 1/11 of 6. 1/11, that would be 6/11. 6/11 minus 5. That gives us a negative answer. We're going to be having some issues in there dealing with that because you cannot take the log of a negative number. So always check your answers to check for extraneous solutions or to check for no solution. Let's take a peek at log base 2 of x plus log base 2 of x minus 6 equals 4. Okay, looking at this left-hand side here, we have addition, so we can combine these through that operation of addition, very similar to a multiplication symbol if you tweak it a little bit. So addition leads us to multiplication. We have log base 2 of x times x minus 6. X squared minus 6x equals 4. Okay, now we are going to change form from log form to an exponential form. So log base 2 to the 4th equals, shoot back across that, x squared minus 6x. Log base 2, that's your base, raised to the 4th power, equals that. 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. Alright, so we get 16 equals x squared minus 6x. We can subtract the 16. 0 equals x squared minus 6x minus 16. Let's change this to a factoring problem now. Well, not change it to, but let's use factoring to solve. So I can factor this. 0 equals x 8, 2. I need more negatives. Positive, 0 product property. If I set this to 0 and solve, I will get x equals 8. If I set this to 0 and solve, I will get x equals negative 2. Negative 2. Now you need to check your answers. Think about this. If I can't take the log of a negative. If I were to make this x value negative 2, I am immediately taking the log of a negative. Extraneous solution. I cannot deal with this. About the 8, I can take the log of 8. I can take the log of 8 minus 6, which is a positive 2. So we are set. We have our singular solution. There are many, many, many more examples that I should probably go through with you. Let's take care of that on another video.
Have a good day.